In this video, we're going to be tackling nodal analysis using Kirchhoff's current law. Now, in this circuit, we are tasked with finding V naught. So how are we going to analyze this circuit to find V naught? Well, remember Kirchhoff's current law. Kirchhoff's current law states that all current going in is equal to all current going out. This can be described as like the amount of cars going in must be equal to the amount of cars going out. If they're not equal, then there's like traffic maybe. But the same is true for current. If there is current going in, there should be an equal amount of current going out. Otherwise, there will be a lot of problems. So, how do we use this here? Well, in nodal analysis, we take a reference frame. So this is V naught, which is the amount of voltage that we have to find. So first, we establish direction. Where is everything going? This voltage source, it goes up. The rule of thumb is always that the direction of current is going from negative to positive. So that's the direction of current that's going in. And then this is going down, as we all know. And this, well, there's no direction, so we'll find that later. The second thing we have to do is to assume outgoing current. So from V naught, this is the V naught, we assume that all current is going out. Why do we assume this? Remember Kirchhoff's current law. All current going in is equal to all current going out. And if all the current is going out, this means that there is no current going in, or the all current going in is equals to zero, which means the sum of all current going out is equal to zero. So that will be useful in analyzing this node. So let's go solving it. From here, let's draw arrows away, going away from V naught or VO, V out, V0, whatever. So let's start from the left. So this is so how do we find the current of this part? This part right here. We don't include the ground because the ground is always zero voltage. Well, remember Ohm's law. Voltage equals current times resistance, or current equals voltage over resistance. There's one voltage source here. This is VO. This is a voltage source. And this is 10 volts. This is an independent voltage source. And this is going in the opposite direction. So it's negative. So it's VO. It's going this way. And since this is facing the other way, this is negative 10 volts. Then the resistance is 1 kilo ohms. So we have to divide it by 1 kilo ohm. This is now resistance. Now, going down, we see 3 milliamperes. Do we need to calculate the current? No, the current is already given to us. So it is just plus 3 milliamperes. Then, going this direction, there are no voltage sources except for VO, which we considered as a voltage source earlier. So that's going to be the voltage. So VO plus VO over what is the resistance, the total resistance going through this path? Well, there's 2 kilo ohms and then there's 1 kilo ohms, and resistances in series is additive. So we have to add both here. And by Kirchhoff's current law, this is all outgoing current. This must be equal to zero. So let's try solving this. If you punch this in a calculator or if you solved it, you will end up with VO being equal to 5.25 volts. So let's try, let's simplify this in order to prove it. So V over 1 is just VO minus 10 volts over 1 is just 10 plus 3 plus VO over 3. All right, so this is going to be negative 7, and transposing it to the side gives us 7, and VO plus V over 3 is 4 over 3 VO. So VO then is 21 over 4, which is exactly this. There's 5.25 volts is the answer for this one. All right. So we've found the basics of nodal analysis. Let's go to a harder question. Here we go. So we are tasked with finding V1 and V2. Now there are two voltage voltages that we have to find. And how are we going to find that? Well, still nodal analysis. So again, let's establish direction. This goes like that from negative to positive. This goes from negative to positive, and of course, this is being it's pointing up. So it's going there. Now, let's assume outgoing current for V1 and V2. So, let's do nodal analysis, what I like to call NDA. It's for V1. So look at V1, look at the left. There's what voltage affects this one? I forgot to write the voltages down, sorry. This is 1 kilo ohm, this is 1 kilo ohm, this is 2 kilo ohms, this is 1 kilo ohm, this is 5 volts, and I think that's it. So, sorry for the mishap, but what is the current flowing through here? We don't know that yet, but we can use Ohm's law in order to find the current going through here. So we know that there's voltage affecting the 1 kilo ohm resistor, and there's also 10 volts in here. So we need to have V1 minus 10 volts, since 10 volts goes in the opposite direction of V1 over 1 kilo ohm. For the second one, going down, we get 1 kilo ohm, and the only thing affecting it is V1. So it must be V1 over 1 kilo ohm. And for the third one, what is affecting this 2 kilo ohm resistor? V1 and V2, but opposite. So we do V1 minus V2 over 2 kilo ohms right here. I hope you understand that V2 is opposite of this, since it is going in the other direction as V1. And this should be equal to 0 due to Kirchhoff's current law. Now, there are two variables here, so we need two equations. This is not enough. We need to do nodal analysis for V2. So, V2, right here, let's go to the left. This is what is affecting this 2 kilo ohm, V2, of course, and V1. So V2 is in this direction. By default, V2 is positive. And then we subtract V1 because it's going in the opposite direction as V2. Then we divide by 2 kilo ohms. Going down here, there is what is affecting this 1 kilo ohm resistor. First off, this V2 is going down, and the 5 voltage source, independent voltage source, also goes down. So they agree on the direction. Therefore, we have to add them together. So V2 plus 5 volts over 1 kilo ohm. And then, and then we have to work with this. What current is going through here? Well, we are being told already that there is 2 milliamperes current going opposite of V2. So we need to subtract 2 milliamperes. And if you're going to input this in a calculator using like mode 5 in my Casio calculator, let's arrange this so that this looks better. So first one, for this, we get 2.5 V1 minus 0.5 V2 equals 10. And for this one, we get negative 0.5 V1 plus 1.5 V2 equals negative 3 milliamperes. Let's remove the labels. There we go. So this is a simultaneous equation. You can multiply 3 here maybe. in order to get that. But if you're going to use the calculator, it's much easier. And since this is engineering anyway, you can use a calculator. Don't be afraid to use the calculator, guys. So we get V1 as 3.86 volts and V2 is negative 0.71 volts. This is the answer. And what does it mean by negative voltage? Well, it just means that the direction of voltage must be opposite. So instead of going out, it must be going in to that. Or maybe the amount going in is outweighs the amount going out. So maybe that's the reason. But whatever the case, it is negative. So there must be a sign convention that is wrong. And that's all for now on nodal analysis. I'll see you on my ongoing series about differential equations. And I hope this helped in your upcoming quiz. I know. Bye bye.